Welcome to 12.5. Our first order of business today is to move on from all of the vector tools we've been developing and actually start talking about some stuff. So today we're going to figure out how to define lines and planes. So we're going to begin with a line. Here is a big old line, which we could call L, I guess. Here's our line L. And we want to figure out how to describe it. Now, you've probably described lines a whole bunch in your life in 2D. One of the issues in 3D, right, is that our normal line equations, right, like, y equals x, that's not a line in 3D. That is a plane. So how do we get just a line? Well, let's go back to the basics. Here I've drawn a line. Let's say we know a single point on the line, which I've called P0 with coordinates x0, y0, z0. And we're actually going to draw a vector that points to it, this vector r0, which, is going to be the position vector of that point. So it'll be the vector x0, y0, z0. So there's one point. Let's say we take a second point also on the line, right? So we've got any other point on our line, P. This is just an arbitrary point, x, y, z, right? We're trying to find another point on our line. Well, we could draw another vector to that point. We'll just call this one the vector r. And this is just the point we're interested in, x, y, z. And we want to figure out how to describe the line that goes through both of those points. Well, one thing you might notice is that we've got these two vectors, r0 and r. And I can actually declare this other vector. I can say, well, what about this vector that runs parallel to my line that connects them? And we'll call this vector, call this vector v. That connects these 2 points. We'll call this vector v. And we can say that, with some confidence that v equals r minus r0. It takes us from r0 over to r. Well, one thing we can note now is if I want to go to any other point on my line, now that I have this vector v, all I need to do is, well, if I want to go a little further out, I can add another v, right? If I want to go this way, I could add some negative v's. Because I have that vector v that's parallel to this line, I can now just move along it. And the effect is r0 is going to take us out to this point that we know to be on our line, and then we can add and subtract v and just move along our line. And so actually we're going to be able to write the equation of this line like this. We're going to be able to write it. The vector equation of our line is going to be any point r that we're interested in on our line we can get to by starting at r0 and adding some scalar multiple of v, r0 plus t times v. That's supposed to be a plus. r0 plus t times v. And you might be looking at this and saying, well, that kind of looks a lot like a form that I already know. It kind of looks a little bit like, y equals b plus x times m. So in this case, you've kind of got your intercept in a sense. You've got like a starting point to go from. You've got a parameter that tells you how far you're going. And then instead of a slope, you have this direction vector, v, that points you where you want to go. That points you where you want to go. All right. So this is what's called the vector equation. Of our line. This t is called the parameter. T is just some parameter that carries us along our line. It tells us how many steps of size v we're taking. It's just some scalar parameter. And as a result, this is what's called a parameterization of our line. Now, it turns out you can write this a different way, right? Let's say that vector v is just, some vector. It's got 3 components, a, b, c. Well, we could break things out. Instead of talking about the whole vectors, we could write them as the 3 components, x, y, z. So from r0, we'll take x0 plus a times t, y0 plus b times t, z0 plus c times t. And these equations together are what's called the parametric form, the parametric equations. And it's important to note that they describe the same line in two different ways. So let's actually try this out. Let's say that I know my 2 points. I got 2 points on my line. Let's say I've got the points. Say I've got the points 2, 2, 3, and 3, negative 5, 3, negative 1, 5, and I want to find the line that connects them. Well, one thing I could do is I could find the vector AB that connects them. So if I do that by doing a little subtraction, 3 minus 2 gives me 1, negative 3, 2. So the vector that connects these 2 points is the vector 1, negative 3, 2. So I could write my equation this way. I could write the equation of my line as r equals 2, 2, 3. Now notice I'm writing this in the vector form, and so I'm using vector notation, not the point, because I want the vector that tells me where the points on my line are to be a vector, plus t times 1, negative 3, 2. I could also do it this way. I could do 2, 2, 3 plus t times negative 1, 3, negative 2. It's the same line, it just, as I move, for my first equation, as I change t, I move one way along the line. For my second equation, as I change t, I move the other way along the line. But it's going to hit all of the same points. I could also do it this way, and you can convince yourself of that. What does t have to be equal to hit point B? I could also start at point B. I could start at point B. I could start at 3, negative 1, 5, plus t times 1, negative 3, 2. So I could start at the other point. I could even do this. I could do 3, negative 1, 5, plus t times 2, negative 6, 4. So there's a really, really, really important idea that we're going to hit all year, which is that parameterizations are not unique. There are an infinite number of ways to parameterize the same line. And it is the same line. It goes through all the same points, right? If I plug in t equals 1 for this first equation, I get point B. If I plug in t equals negative 1 for the second equation, I get also point B. If I plug in, well, this one starts at point B, so if I plug in t equals 0, I get point B, or I could do t equals negative 1 to get back to point A. This one, I guess I would have to take t equals negative 1/2 to get back to point A. But the idea is, all of these describe the same line. They're just going to move kind of, if you like, different speeds along the line. Some of them are going to move in one direction, some of them are going to move in the other direction, or faster or slower. But they all hit all the same points. And so for any given problem we do, we're going to find out that the parameterization doesn't really matter. You can choose whatever parameterization you want and still solve the problem. So usually we'll stick to a relatively simple one, but anything that does the job works. All right, we turn our attention now to how to define a plane in 3D. Now, you already know that you can write some equations out, but what if I give you a set of points and I want you to tell me what's the plane that goes through them, or to write the equation of a plane? Well, we have a lot of different options, and depending on what you've seen before, you might be familiar with some of them. We could use 3 non-collinear points, 3 points to define a plane, as long as they're not in a line. We could use 2 vectors to define a plane, but we're actually going to use a somewhat unconventional choice, which will make a lot of sense soon. We're going to use 1 point, so we'll have 1 point that we know to be in the plane. And we're going to choose a normal vector. And normal is just another math word that means perpendicular, just like perpendicular or orthogonal. Normal, in this case, means a vector perpendicular to our plane. And usually this is called n for the normal vector. So here I've drawn a plane, just some random plane, and you'll notice I've got 1 point that I know, which is kind of like with our line, p0, which I'm going to call x0, y0, z0. And I've got the position vector of that point, r0, which is, x0, y0, z0. And then I'm going to find some other point in space, x, y, z, and I'm going to say, if that point's on my plane, what can I say about that? How can I figure out whether this other point is on my plane? Well, similar to the line, we're going to take this random point x, y, z, and we're going to put in this little displacement vector. Or we're going to try to. We're going to put in this displacement vector. And I'm going to call this displacement vector, well, this displacement vector is r minus r0. So that displacement vector, r minus r0, is, x minus x0, y minus y0, and so on. Because this point r is just some random point x, y, z on our plane. It's not a fixed point, it's every other point on our plane. Okay, well, this vector, hopefully it's clear, because it connects 2 points that are in our plane. We know r0 is in our plane, and this other point r, or p0 and this other point p, we know they're both in our plane. Hopefully it's clear that r minus r0 lies in the plane. And as a result, if we have this normal vector to the plane that's perpendicular to the plane, we can say with some degree of confidence, in fact total confidence, that r and r0, that n and this vector r minus r0 are perpendicular to each other. Now, we do have a great tool already in our toolbox to declare things being perpendicular, which is to say, we can say with utter confidence that n, or whatever our normal vector is, dotted with r minus r0 has to equal 0. And this is actually how we define a plane, and you might be looking at that and saying, Mr. Bates, I don't really understand what that means. I don't really know what to do with that. So let's bring it up to the top here and do a little bit more. Let's say we happen to know what the normal vector is, right? Let's just say it's some vector a, b, c. Let's actually take this dot product, because we know what r minus r0 is. If we actually take that dot product, what we get is a times x minus x0 plus b y minus y0 plus z plus c, z minus z0 equals 0. Equals 0. And this is an actual equation we can write down in x, y, and z to figure out what our points are. Now, we can actually rewrite this a little bit. If you imagine multiplying it out and figuring out what a times x0, b times y0 and stuff, we can also write this a slightly different way. We can write this as ax plus by plus cz equals some number d. And what's neat about this is probably how you've seen planes written so far. You've probably seen them as written, like 3x plus 2y plus 2z equals 7 or whatever. And what you'll notice about this, one thing that's really super cool, is that look what these coefficients mean. 3x plus 2y plus 2z, a, b, and c. The coefficients in the equation are the components of the normal vector. And that's a really powerful tool. If I hand you a plane, I'm like, the plane x minus y plus 5z equals 2. You can immediately tell me, aha, Mr. Bates, I know that the normal vector to this plane is 1, -1, 5. That is the normal vector to the plane. And knowing the normal vector to a plane can be extremely useful. And we're going to now define a plane in our worked example. I'm going to give you 3 points, and we're going to work to figure out how to define a plane. Let's look at a worked example. Let's try to figure out what the equation of the plane is that goes through these 3 points, 1, 1, 1, 3, 0, 4, and -1, 5, 2. Now, remember, we've got some points in our plane, and our big challenge here is to figure out what our normal vector is. If we can figure out what our normal vector is, then we can figure out what our equation is. Well, if only we had a way to find a vector that was consistently normal or consistently at right angles to other things. Oh wait, we do. The cross product. So what we're going to do is we're going to take our 3 points, and we are going to find the vectors that connect them. And then we're going to take the cross product to find a normal vector to both of them. So let's go ahead and take a look at that. Let's first of all find the vectors that connect these things. If I find the vector from A to B, that should be the vector 2, negative 1, 3. And from A to C should be the vector negative 2, 4, 1. So let's go ahead and set up the cross product AB cross AC. I hat, J hat, K hat. 2, negative 1, 3, negative 2, 4, 1. We can go ahead and expand that with our matrix of minors. I hat, negative 1, 3, 4, 1, minus J hat, 2, 3, negative 2, 1, plus K hat. I'll do this down here. And that's 2, negative 1, negative 2, 4. So that's going to be, let's see, I hat times negative 1 minus 12 minus J hat 2 plus 6 plus K hat 8 minus 2, because negative 2 times negative 1 is positive 2. So we end up with this vector. We end up with the vector negative 13, negative 8, 6. And just because, remember, if we've got one normal vector to our plane, any scalar multiple of that works. I don't like things with leading negatives. It's just a personal bias of mine. So I'm going to instead use the vector 13, 8, negative 6. Now that we have the normal vector, we should just be able to plug it into our equation like so. We should be able to just plug it into our equation. So let's try that. So we should get 13, except with a marker that seems to be functioning a little bit better today. There we go, 13. Now, which of our 3 points do we want to use for this? It actually shouldn't matter. So I'm just going to take A. We'll double check that. X minus 1 plus 8 y minus 1 minus 6 z minus 1 equals 0. Or I could rewrite this as 13x plus 8y minus 6z equals, and now if I do 13 plus 8 is 21, minus 6 is 15. And let's just double check that that works. If I plug in here, I get 13 times 3 is 39, minus 24 is 15. And if I use point C, I get negative 13 plus 40, which is 27 minus 12, which gives me 15. So this is the equation of the plane through those 3 points.